How many ways are there to arrange A, B, and C?
6.
Right, we did this last time, right? This is exactly what we did last time. And I want to I'm going to brute force it, right? Just the same way we did last time. You could do A, B, C. You could do A, C, B. You could do B, A, C, or you could do B, C, A. You could do C, A, B, or you could do C, B, A, and that exhausts all the possible arrangements or permutations of these 3 letters. Okay, so that's just review. And yes, the number of ways of doing it is 3 factorial, because there's 3 things. This is what we talked about last time, 3 factorial. Okay. What about this? What did you guys get for that?
3. I got 3.
You got 3?
Well, unless you like switching them, you could say that
you could say, right? Like if you said, so like what you could think about is, well, if you gave me 3 letters, and if I took each one of these letters and put them in 3 boxes, let's say this is a red box, and this is a blue box, and this is a green box, and I put the first A in there, and then I put the second A in here, and then I put the third B in there, then I could go through and arrange all of these things that way, right?
Yeah.
And then you would end up with 3 factorial different arrangements of these 3 different things, but then it would turn out that, and what you would have here is this same setup. The only difference is, I guess, instead of C's, you would have A's. So you would have A, B, A. A, A, B. Here you would have B, A, A. Here you would have B, A, A. Here you would have A, B, and here you would have A, B, A. Right?
And there I agree.
So, yes, technically, I guess, there are 3 factorial ways of doing it. But you could see that this and that are the same thing. That this one and this one are the same thing. These are all indistinguishable, right? This one is indistinguishable from this one. This one is indistinguishable from this one. There, right? Does that make sense when I use that word, right? So let's actually give it a definition. A distinguishable permutation. D-I-S, not a distinguishable, and you can't have a distinguishable permutation. It's kind of like you can't have a twin, right? Like the twin of what, right? So like this would be a distinguishable permutations. You have to be referring to at least 2 of them. Distinguishable permutations are arrangements. Or arrangements which cannot be obtained from each other, and yes, I know each other is 2 words, each other, by rearranging like objects. Like objects. So in the first case, all of our objects were distinct, and so that doesn't really matter here. Here we have 2 like objects. The A and the A they're the same type of object, right? And so a distinguishable permutation would be like this one and this one. A, B, A. And A, B are distinguishable. I don't have room. They're distinguishable because if you rearrange the like objects, you swap the A and the A, you still don't get this, right? You swap the A and the A here, and you still don't get that, so they are distinguishable. However, these are 2 different permutations, technically, because you could imagine if we took the A, and the B and put them in the red, the green, and the blue boxes, and then did all of these, well, it turns out that BAA and BAA are Is it non or un? Non-distinguishable. Non or non-distinguishable. Why? Because if you rearrange the like objects in the string, here's the string BAA, you rearrange the like ones, well, it's the same thing as that, right? And so they're non-distinguishable. Okay? Okay. Questions on this? It makes a lot of sense. Like, we have this nifty, like, rigorous definition of that, but it makes perfect sense. Like, I really didn't need to write this on the board, and just by looking at this, you knew what I was talking about, right? Yeah, like, you could distinguish between them. You can't distinguish between that and that. They're non-distinguishable. But this one and this one are distinguishable, because if you rearrange the ones that are the same, you can't get... Okay, all right. Okay, great. Oh, did I want to leave that up there? I think I did. Whatever. Okay, so let's get a formula. Because we have a nice formula for this, right? 3 factorial. You have 3 distinct things, 3 factorial ways to arrange it. What about this?
3 factorial over 2.
And that's over it. Yes, and that happens to be over 2, but it's not just over 2.
2 factorial.
2 factorial, and let's see why. So the ones that I had up here were A, B, A, B, B, A, B, A, B, and A, B, A. So if you think about it, we want So we want a formula for the number of distinguishable permutations. And if you look at this, right, these two are indistinguishable. I'm going to put boxes around them. These two are indistinguishable. And another shape, how about a diamond? There we go. And these two are indistinguishable. Why is that? Well, the number of things that we have, right? In this case, the number of repeats that we have is 2. And so you could think about this as like, well, if I have 2 repeats here, how many ways can I arrange those repeats? Well, since there's 2 of them, I could arrange these repeats in 2 factorial different ways, right? And yes, indeed, for 2 factorial, which happens to be 2, gives you those 2 non-distinguishable permutations. If you have ABA, since there's 2 repeats here, there's 2 factorial ways of rearranging them. And you end up with the exact same thing, right? Same thing here. Does everybody understand what I'm saying here? Yeah. So, okay. We want a formula. We want the total number of ways to arrange distinguishable permutations. And what we're going to do is start with this specific example. So what we want is the number of ways to arrange distinguishable permutations of 3 things, given that. Well, you're going to have to wait, buddy. Given that 2 of these 3 are the same. This is our goal. And what we're going to do is we're going to get a formula for that in this specific case. Then we're going to generalize and say instead of 3 things, we're going to have n things. And instead of 2 of them being the same type of thing, we're going to say that r of them are of the same type. But we're going to start simple with this, okay? So let's use the fundamental counting principle. Okay? So we have these 2. One way of thinking about this problem is we have 2 events. Event 1 is that you have a permutation, right? And the first event is that permutation is distinguishable. E2 is that, and you see what I'm saying? Like I just said, like you have to have two permutations to be able to call them distinguishable or whatever. This is where this kind of breaks down. But you'll see what I'm about to do, and it'll make sense. We really don't need to write this stuff down. This is, the permutation is non-distinguishable. So in other words, we're talking about these 6 right here. These 6. And we know that and so, let's think about it this way. So the same way we did this last time, M1 is the number of ways that you could have distinguishable permutations. Right? Here, this is going to be the number of ways, or the total number of non-distinguishable permutations. Okay? And then, so then all of them, this times this, should be the total number of permutations. Does that make sense? So M1 times M2 should be the total number of permutations.
Puffins now. Puffins?
Yes, you could have puffins. Okay? So does that make sense? All of this is, like, we really didn't need to write all this down, but does it make sense to say, well, if you want the total number of permutations, if you multiply the number that are distinguished, how many ways you could have distinguishable ones, times how many ways you could have indistinguishable ones, you get the total number. Does that make sense? Okay, so let's think about this. We know that the total number of permutations of 3 things is?
There you go. 3 factorial.
3 factorial. We know that the number of non-distinct, and this is where this is going to, because what we're looking for is the number of distinguishable ones. Right, so I'm going to rewrite this as number distinguishable times the number of non-distinguishable. In other words, the repeats. And if you think about it, since there's only 2 things, then there are 2 factorial ways of arranging any one of these so that it is non-distinguishable. And so it works out to be this right here. And so the number that we're looking for, the number of distinguishable permutations, is 3 factorial divided by 2 factorial, which is 3, which is what we said at the beginning when we did brute force, right?
Yeah.
Everybody follow that?
Yeah.
It's not too hard to see in that case. Now, ooh, did I do this? Ooh, wait, just let me make sure. Okay, yes, this is what I wanted to do. Okay. So let's leave that up. We're still working on this. Because now we have this one specific case. We might want to just generalize, but let's just to make sure that we're all on the same page here. Let's say we have these types of strings here. So in other words, instead of having A, B, and C that we're trying to arrange, or in this case A, and B, it looks like we're trying to arrange A, B, let's use all my fingers here. We have A, B, another B, a C, another B, a D, an E, another B, and another B. So now we have 9 things that we want to arrange, but 5 of them are the same type of thing. And what I mean by this is, like, in the same way as before, right, we ended up with like an A, B, and then later on we had another A, B, and we said that they're non-distinguishable. It should be clear that if I swap any of these B's with each other, what we end up with is another non-distinguishable permutation. And how many ways can I rearrange those B's?
5 factorial.
There's 5, because there's 5 of them, then there's 5 factorial ways of, given one of these, give me any of your permutations of those things, there's 5 factorial ways of rearranging them so that it is non-distinguishable from any of those others. Right? Okay, alright, so we're ready to do this more generally now. And so slightly more generally, if R is a number, if R objects in a collection of n objects are alike. Okay, so in other words, R in this case would be 2, right? 2 of those, here's your collection of n objects, so n would be 3. You have a total number of 3 of them. N is 3. Here, R is 2 because 2 of them are alike. They're of the same kind. Yeah? Okay. Are alike. And the rest are different. Then we're going to do the same kind of thing. The number of distinct permutations times the number of non-distinct permutations is equal to
n factorial.
n factorial, right? The total number of permutations, which in this case is n factorial, because you have n objects and you can arrange, right? We're imagining that we're putting them in n different colored boxes and doing the arrangements, and then we're going to take everything out. But a bunch of those are going to be non-distinct. How many of them are non-distinct?
R factorial.
R factorial, because it's the same kind of thing. When we had a bunch of B's, and then a C, a D, and a B, you could say, well, however many B's you have, there are R factorial ways of rearranging them. And so, yes, R of them are the same, and so you have R factorial ways. And so then, the number of distinct ones, just like we found before, the number of distinct permutations is the total number of things divided by, the total number of things factorial, divided by the repeats factorial. And that agrees with what we had here, right? Okay, now, even more generally, like this is a nice thing to remember, but even more generally, we could just, if you have to remember something like this, it would pay off to just remember this next thing that I'm going to write down. So I'm going to get rid of all this. Can I get rid of all this? Yeah. Okay. So if you want to remember stuff, this would be the thing that I remember. Okay. So. I did write this down. Okay. More generally, suppose that we have several collections of non-distinguishable objects. So something like this. A, B, C. Here's one permutation of a bunch of letters. So, yikes. Okay? But let's just think about this. So, this is just one permutation. This would be if I said, how many ways are there to arrange? I would have had 1, 2, 3, 4, 5, 6 A's. 1, 2, 3, 4, 5, 6 A's. 1, 2 B's. These are all theirs. And then 1, 2 C's. 1, 2 C's. 2 D's. 1 E and 1 F, it looks like. Looks like. Is that right? That's right. Okay. We want to say how many ways to arrange. And then you do that with all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there would be 14 factorial ways of getting strings like this. But a bunch of them would be repeats. Right? And not just one way. Not just the A's with the A's, there are 1, 2, 3, 4, 5, 6 factorial ways that you could rearrange these A's and they would have been the same thing. There are 1, 2 factorial ways of doing the B's, and so on and so forth, so that you end up with a ton of these repeats. Okay? So, since that's the case, we could play the same kind of game and say, well, again, the number of distinct times the number of non-distinct permutations is going to equal the total number of permutations, which, since we have 14 things, is what? 14 factorial. But now, what do we do for the non-distinct ones? What do you think we do? How many non-distinct permutations are there for this specific example? So, and let's just count up. We have 6 A's, 2 B's, 2 C's, 2 D's, 1 E, and 1 F.
But the E and F are distinct.
D, E, and F are just each one. So, how many ways would there be to rearrange these 6 A's?
6 factorial.
How many ways to do those B's?
2 factorial.
And so we're just multiplying them all together. How many ways with the C's? 2 factorial times 2 factorial. 'Cause again, I'm kind of using the counting principle in here too, right? Because the number of non-distinct ways, well, it could be non-distinct because of this, it could be non-distinct because of this, it could be non-distinct because of this and this, right? So those are all of the events, right?
Yeah. Okay.
And so we multiply all the number of possible ways that those events could occur. And that is all the ways that those events could occur. So altogether now, the number of distinct permutations is n factorial over 6, 2, 2, 2. And if we really wanted to, we could say, well, what about these? Well, just go ahead and throw them in there. Why not? 1 factorial, right? And that's nice because that'll give you a nifty formula that you could use, which we're going to see in just a second. Okay, so in general now, can I get rid of this?
Yeah.
Everybody got this? Like, I find a lot of this hard to believe, quite frankly, but
Yeah.
it does work. I mean, if you really want to, if you're interested in this, I suggest that you sit down and really convince yourself of this stuff, if you're interested. Otherwise, okay. So here we go. Now this is the big takeaway. If in a collection of n objects, in one of them, in one are of a kind. So in this case, 6 of them were of a kind, and 2 of another kind. So N2 would be 2 in this case, because we have 2 of the same types, and so on, up to NK, how did I write that? Are of a kind. Then the number of distinguishable permutations is equal to n factorial, n1 factorial, n2 factorial, all the way up to nk factorial. And you have to have it where n, the total number, is equal to all of these guys. Okay. Does that make sense? That, right, like the same way that if you counted all of these up, 6 plus 2 plus 2 plus 2 plus 1 plus 1 was indeed equal to 14. This is just saying you can't leave any of them out, basically. Yeah. So then, the way you find the distinguishable permutations is by doing this. And this is what we just did with the case with 14, and where you had 6, 2, we had a 2 and another 2, and then I threw in the 1s for good measure so that it fits in this nice nifty formula. Okay? Everybody got that? Okay. I hate this stuff. So, alright. But that's good to know. Still good to know. Okay? Can I get rid of all this? Okay. So here we go. Just good stuff to know. The hard part is figuring out when to use that. Because we're about to learn something completely different. And what we've been talking about up till now are permutations. And permutations, they are concerned with the order. They are concerned with the order. A combination. This is the thing we're about to learn about. Something we've been learning about permutations. Now we're going to be talking about combinations. A combination of R elements. So R things of a collection of N objects. Okay? So you have N, and of course, R here at biggest can be N, right? you can't be talking about a certain number of elements of a bigger thing and have it being bigger than that thing, right? Like when we're talking about A, B, and C, you can't say, well, let's take 4 elements from there. Well, you can't. You cannot create ex nihilo. Okay, so here we go. A combination of R elements out of a collection of N objects is a subset. And this is the key there. It's a subset that contains R objects. Subsets don't care about order, right? Because the set 5, 3, 2 is exactly the same set as 2, 5, 3. Right? So this is this is the key here. This is the key. Order doesn't matter.
Combination.
So a combination order doesn't matter. And this is the key for pretty much all of the homework that you're going to be doing. Is in each one of these problems you have to say, well, is the thing that they're asking me, does the order matter? Or does it not? We'll talk about that in a minute, but that's what so much of this comes down to. Okay? I'm sorry, give me a second. Yeah, that's what I wanted to do. Okay, now. Right now, here's an example. And what I'm about to do, the order does matter, because the way I'm going to ask it, I'll tell you that. Given 4 things. I cannot spell today. E-C-T-S. Given 4 objects, call them A, B, C, and D. How many ways to arrange 2 of them? Think back to your most recent homework, what we talked about last time.
Or it could be, yeah. Oh, right.
It's 4, it's 4 times 3.
Or 4 factorial over 4 minus 2 factorial.
There you go, right? So this is what we talked about last time. That's how many ways there are to do it. Yeah? Let's write them all out. So we could do that with, let's say the ones where A comes first. We have AB, we have AC, and we have AD. Yeah? Now the ones where B comes first are BA, BC, and BD. We have the ones where C comes first. CA, CB, and CD. Now the ones where D comes first are D, A, D, B, and D. Did I mess something up? No? Okay, okay. And D, C. Yeah? That should be all 12 of them.
Yeah.
And let's just see. That's 4 factorial over 2 factorial, which is 4 times 3 times 2 factorial over 2 factorial. Those guys cancel. It's 4 times 3, which is what you said, which is 12, and I think those are 12 things. Yeah? Now that's where order matters. And you could think about that as like, how many words can you spell with 2 of these things? Well, those are all of the words you could spell with 2 of those, by taking just 2 of them out. But if you imagine that now we don't care about how can you arrange them, you're just going to take 2 of them and throw them in a bag. And if you just throw 2 of them in a bag, A and B, well, their order doesn't matter. It could be BA or it could be AB. And so this one and where is it? This one are equivalent. They're the exact same thing. Because they're in a bag. You shake up the bag, it doesn't matter which one came first. Order doesn't matter. And so now we're asking not how many ways to arrange 2 of them, but we're asking how many ways to choose 2 of them. And parenthetically, where order doesn't matter.
So then it would be 4 factorial over 1 factorial, 2 factorial times 4 minus. It's just to choose.
Okay.
Can we?
So let's just see here. I want to actually look at this and just see, right? AC and CA pair off. So here's 1. Here's 2. AD and DA pair off, so that's 3. BC and CB pair off, so that's 4. BD and DB pair off, that's 5. CD and DC pair off. And so that's 6. The total number would be 6.
So just minus it.
No, we're not minusing anything. So what I want to do, so that I don't mess this up, because what I will do, I just happen to know, just like everything we've talked about up until now, something tells me it's not minusing.
Yeah.
Something tells me it's either multiply or divide. And I know I'm going to mess it up if I mess this up. So what I'm going to do is come back to say, well, oh no, we're going to do that in a minute. We're going to do that in a minute. I'm sorry. So, okay. Another way of thinking about this is, since we've just chosen 2 things, here's 2 things, how many ways can you rearrange those 2 things and have them? 2. There's 2. Well, okay. Now, what about arranging 3 things?
6.
Yes, and so let's think about it this way. So now, instead of saying, given 4 objects, A, B, C, and D, how many ways are there to choose 3 of them? And so, let's think about this. So first off, let's take a step back. Instead of saying choose, let's do this the same way that we did before. Let's say arrange 3 of them. So this was when we arranged 4 of them. This is arrange 2. Right? That's what we derived in order to arrange 2.
So it'd just be 4 minus 3 at the bottom.
Oh, down here you mean?
Yeah.
Yes. So how many ways to arrange 4? So now we are arrange 3 of them. You say it's 4 factorial over what?
4 minus 3 factorial.
4 minus 3 factorial. And this is just what we learned last time, right? Okay, which is 1 factorial. So it's 4 times 3 times 2. It should be 24. I'm not going to write out all 24 of those. But here's the thing to notice, is that let's just take one selection of them. And let's just say, so we can arrange 3 of them. Let's say it's these 3 that are being arranged. We would have, one of them would be ABC, one of them would be ACB, one of them would be BAC, another one would be BCA, another one would be CAB, and the only one that's left would be this right here. How many of them are there? 6, which is, how could you derive that without actually counting that?
3 factorial.
3 factorial. So if you imagine that we had all of the arrangements out there, right? All of the all 24 of arranging 3 of them, it would turn out that for each one of these groups that you pulled out, like I chose A, B, and C, the same thing would have been true if I chose B, C, and D. Or if I chose A, C, and D. Or if I chose D, A, and B, or whatever, right? In every case, once you take 3, there are 3 factorial ways of writing them, which, when you go to talk about choosing them, all of these are exactly the same. Once you throw that in your bag, the order doesn't matter, right? Right?
Yeah.
So this is what I'm getting at. This is what I'm getting at right here. I want to do it with this one first. Okay, so let's go back to where we talked about choosing 2 of them. We could say, well, let's think about this. The number of ways to choose 2 times the number of ways to arrange those 2 should be the number of arrangements of this, right? Right? The number of ways to arrange 2 of these things would be, it's the same thing. And if you think about how we did this, right? I said, well, let me just take 2 of them. And then I said, well, there's that, and there's another one, BA, okay? Let's take another 2. How about A and C? Okay, well, there's also CA. Let's take another 2. There's BC, and there's also CB, right? And we could get all 12 of them this way. And if you think about it, what is that? Well, it's the number of ways to take 2 of them out times the number of ways to arrange each of them, which in this case happens to be 2, but that's 2 factorial. And so this was, we said this was P for 2. Yeah, it was this. Right? The number of ways to arrange them is the same thing as the number of ways to choose 2 of them times the number of ways to arrange those 2. And what was the number of ways to arrange 2 things?
12.
I'm sorry.
12.
No. Now you've taken 2.
Oh.
Those very 2.
Oh.
Those 2 that you've taken.
There's 2.
There's
2. 1.
2.
Wait.
Not 2. 2.
2 factorial.
2 factorial, okay? So the number of ways to choose 2 times the number of ways to arrange those 2 very things is 2 factorial. This was this. Yeah?
Yeah.
And so therefore, the number of ways to choose.
So it's just
Isn't that the end?
4.
Choose K?
Yeah.
Oh, that's why we called it N choose K. So this is 4 choose 2. Isn't it?
Yeah.
Yeah. That's kind of cool. I think that's kind of cool. I mean, I hate this stuff, but I think that's kind of cool. This is the same thing as the binomial coefficient. This is where it comes from. Another way you could say that is, you know, like kind of like you did. You said, well, it's minus 2, or is it divide by 2? It is divide by 2, but it's not divide by 2. It's divide by 2 factorial. So let's do it now with 3. But now we want to find the total number of ways.
Yeah.
Yeah, let's do this. We want to find the total number of ways to choose 3 things from this set of 4 things. Well, it should be the number of ways to arrange those 3 things, right? Well, that times that should be this right here. All the permutations for 3 right there, right? Does that make sense? If you take all the permutations of 3 of these things, it's that many of them, it's 24. And a bunch of them will be repeats. And as we saw before when I went through and did this, A, B, C, C, A, B, A, C, B, right? There's 6 of them. There's a total of 6 of them, but it's not 6, it's 3 factorial. Because now that you've taken your 3, there are 3 factorial ways of rearranging them. And so another way of calculating this number would be, well, if we could find all the number of ways to just take 3 things out. And then we find all the ways of, now that you've taken those 3 things, how many permutations do you get? Well, it's 3 factorial. And so then that should be the total number of permutations that you would get. That's what this is. That's what this counting principle tells us. And so then the number of ways to choose 3 times how many ways are there to arrange those 3 things?
3 factorial.
There you go. That's this, right? The number of ways to permute, the number of permutations of 3 things taken out of 4 things is 4 factorial over 4 minus 3 factorial. And so then, the number of ways to choose 3 from 4 things is equal to 4 factorial over 3 factorial over 4 minus 3 factorial. Which is, this is why we called it 4 choose 3. When I first wrote that up there, and I wrote like on this very board the other day, when I wrote n choose k, did that just seem really crazy? Like, why would you call it that? This is why you call it that. Because if you have 4 things and you choose 3 of them, that's how many ways there are to do it. Right there. Turns out to be 4. But you could calculate that. Okay? Okay, so in general. Now the same way that your book uses P, N, K, right, or NR, I'm going to do the same thing here. Can I get rid of all of this stuff here?
Yeah.
Okay. So your book in this section does this. Instead of P, they use C, N, R. Which, by the way, is the same thing as N choose R. Okay? N choose R. Only they call it combination. So you could read this as permutation in R. You could read this as combination in R. Sometimes you will even see this as NPR and then whatever your things happen to be, like a 4 and a 3. Like in calculators, very often, that's the symbol that's used, NPR. In calculators here, NCR is the symbol that's used. Sometimes it's NCK also, and then you plug in your numbers like 5, 2, or whatever. It's all the same thing, and it's all really the binomial coefficient right here. This is the binomial coefficient, and it is equal to n, r, n minus r. This is one you want to commit to memory for the rest of your life, right here. This is something you absolutely, absolutely want to do. But this is when order does not matter. And this is the key here. If the order of the selection is important, use a permutation. If the order does not matter, then use a combination. So let's see an example of when we want to use a combination. Okay. So, no, that's where you want to use permutation. I'm sorry, I thought that I had one singled out for that. I don't. So we're going to use this here. I hate this stuff. I'm sorry. Just that. Okay. Well, yeah. I'll just make one up. Okay. So here's an example. I'm sorry I didn't have something prepped for this. I planned on going somewhere else, but since we just did this, I do want to do an example on this. So let's say there are 5 boys and 6 girls in a class, how many ways can they elect a president and vice president if one must be a boy and the other a girl? Okay, so, and this is kind of a bad one. This one's kind of easy actually, and we don't even need this because I mean, there's 5. You can just think about here's president, here's vice president. So one of the ways would be any 5 of the boys could be president. So there's 5 possibilities. Times any 6 of the girls could be there. That's one way you could do it. Another way you could do it is that the president could be a girl, and so there's 6 ways. And then the vice president would be to choose one of them.
Oh.
Yeah, and you see, so I'm sorry. I'm really sorry. I should have come up with a better one here. Let's do it this way. There are 20 people in a room. Three people are needed to clean the kitchen. How many ways can these folks be selected?
Just be 20 choose
20
3.
choose
That's
3.
That's it. It's that easy, okay? But I'm glad I did this because watch. Okay, so yes, 20 choose 3. That's how many ways. And you could write that as 20 factorial over 3 factorial. 20 minus 3 is what, 17 factorial? So that's 20 times 19 times 18 all over 3 factorial, which is 3 times 2 times 1. We could reduce this, and I did it that way because that divides that divides that, blah, blah, blah. Okay? That's one way of doing it. Now watch this. Three people are needed. How about 3 people are elected as president, vice president, and treasurer. Now, does order matter?
Yeah.
So before, all we were doing, those 3 people were just going to be on a cleanup crew. And you could think about, you took those 3 people and just shoved them in a bag. It didn't matter who came first or who came second.
Yeah.
Here, now you could think about this as we are going to take, there's 20 people, and we need to put one of them in a bin called president. Another one needs to be put in a bin called vice president. And another needs to be put in a bin called treasurer. How many ways are there? Well, that's an order. Even though we don't think about it's like, I guess there is an order, like president is above vice president. But really, like, this part does not matter, right? This part does matter, right? Whereas before, if they're just needed for a cleanup crew, that doesn't matter. So what would this be?
20 factorial over 3 factorial.
Yes, it would be P23. So that would be 20 factorial over 3 factorial. Okay? Yeah, if you're like me, you hate this. Like, I hate it so much. But yeah, that's the idea, right? Order, and it's like, what do you mean order? Well, if you have like specific positions, then that does matter, right? then you could think about those as an order. You could think about, well, whoever's first we'll call president, whoever's second we'll call vice president, whoever's third we'll call blah, blah, blah. Okay? If the order doesn't matter, if they're all going to be equivalent, if they're all in the same cleanup crew, that won't matter. Okay, so we will do this one. Here's number 12. Find the number of distinct permutations. Number of distinct permutations of the letters of the word moon. So in other words, right, like I could rearrange this. One of those permutations would be N-O-M-O, right?
Yeah.
Another one would be M-O-O-N. Another one would be M-O-O-N. Oh, I switched those two, but that's not distinct, is it?
Yeah.
Right? Okay, so that's what this is getting at. So what would it be?
4 factorial over 2 factorial.
4 factorial over 2 factorial times, nice, yeah. And you could forget the ones, who cares, right? But that's, like, technically, if you want to keep something in mind, that's how you do it. For each one of those, you count the numbers of things, and so that's what it would be. Which would be 4 times 3, I think, which is 12. Which kind of blows, like, really? You had 12 distinct permutations of those letters? Huh, I wouldn't have thought that, but okay. I'm not going to write them all out, but that's, yeah. Okay, so that's it. Again, this is going to be a struggle, probably. 27, use a quadratic at some point, or, I mean, you can just brute force. Please don't brute force it. Like, come on. Yeah, and then the rest, there are, the examples in the section roughly follow, like they will roughly give you an idea of how to do some of these that you may not see immediately. Okay. Oh, we have 2 minutes. There's one more thing I wanted to talk about. Oh, we're going to do it. You're going to read this anyway, but I think this is really cool. Let's say you have a set of n things. Okay, so you have some set of n things, and we go A, B, whatever, and there's n of them. N, whatever, right? And what we want to know is how many distinct subsets are there. So, for instance, one of the subsets, and this is something to note, is that the empty subset is always a subset of every set. So that's one of them. Okay. Another one would be just the set A.
Okay.
Another one would just be B, and so on and so forth. Another one would be AB. Another one would be AC, and so on and so forth. But notice that BA is the same thing as AB, so you're not going to count him again. Okay. Okay, so let's think about this. There's n things. Are we talking about a permutation or a combination? Combination.
Combination,
because the order doesn't matter. We're not going to recount CA here. We're not talking about the number of ways to permute all of these things. We're just saying, okay. So in other words, what we want is we're going to think about this. You have n things, and I'm going to do lowercase n. You have n things. How many ways are there to choose 0 of them?
1.
Well, yeah, but there's n choose 0. How many ways are there to choose one of them? N choose 1. And so how many ways are there to choose 2 of them? And choose 2, and so on and so forth. So then all of the this is one subset, this is n subsets, this would be n choose 2 subsets, and so then the total number of subsets,
just all those added together.
Yes, added together. All the way up to n choose n. What is that?
That's just 1. N choose it. Oh.
No, the whole thing. What is that sum?
And
does it look familiar?
binomial.
Do
we do it?
And so, yeah, this looks a lot like if we had n0, you would have an x to the 0, y to the n minus 0. You would have here, you would have n choose 1, you'd have an x to the 1, y to the n minus 1, plus all the way up to the last one where you have n choose n, x to the
and y to the
y to the 0
Oh.
in minus n. Yeah. You'd have all of those. But in this case, what does that mean that x and y both have to be? And oh, and by the way, that would be, in other words, if you have x plus y to the nth power. That's what this would be. Yes?
Yeah.
Everybody buy that? Remember, that's the binomial theorem. Here's this.
Yeah.
That we proved it. We beat that horse over and over. And so, that's this. What numbers can I plug in to make this equal to that?
To me. Oh, zeros.
If I plug
Oh,
in
no,
a
ones,
0,
ones.
then that's gone. So
Yeah.
what do they both have to be?
1.
X has to be a 1,
So 2 to the n.
and Y has to be a 1.
Oh.
And so,
That's weird.
2 to the n, that's how many subsets there are of n things. I think that's really cool. That's a really cool thing. And you could check this, by the way. How many subsets are there of 3 things? Now, it says that it should be 2 to the 3. It should be 8. And we could just check. Here's one of them, the empty set. Okay. Here's one, A. Here's another, B. Here's another, C. Now we need all the ones with 2. So we have AB, we have AC, and we have BC.
Oh, but the other. Yeah, okay.
Because all the others, when you flip them, they're the same thing. So we're not going to count them again. We're just going to count them that one time. And then finally, we have the entire set, ABC. Because a subset is, every set is a subset of itself, technically. So you have these weird bits right here. You have the empty set, which is always a subset. You have the whole set, which is always a subset. And so there's a total of 8. Hey, it works. That's interesting. But that's really cool. I think that's really cool. So that's also in your book, so you don't really need to read that. But okay, that's all I got, guys.